Hi there, my name is Aaron Lanchman. I'm a professor of electrical engineering at Georgia Tech, and this is my quarantine hair. And I would like to welcome you to ECE3084 Signals and Systems. This is lecture number 38. So let's solve a first order differential equation. I'll have y dot plus 10y, and on the input side on the right, we'll have 4 sine 2t ut. Let's use the pre-initial condition with y of 0, not forgetting that little minus, equals 1. All right, so let me take the Laplace transform. I'll have s big Y of s. I'll need to subtract the pre-initial condition, which here is 1, and I'll have plus 10 big Y of s. Let's see, and taking the Laplace transform here, I'll have 4 from the constant in front. Then I'll have 2 over s squared plus 2 squared, which is 4, and that just comes from the Laplace transform of sine 2t ut. So let me put everything with a big Y of s on one side, so I'll have s plus 10. And then on the right, moving the minus 1 over, I'll have 1 plus 8 over s squared plus 4. And now if I imagine rewriting this 1 here as s squared plus 4 over s squared plus 4, I can then divide by the s plus 10 here and write y of s is equal to s squared plus 4 plus 8 all over s squared plus 4 times s plus 10. So now the Laplace transform I will be expanding, well, 8 plus 4 is 12, so there's no mystery here. Let me write out the partial fraction expansion as a over s minus 2j plus b over s plus 2j. And as I mentioned in the last lecture, a and b, we'll find out, are going to be complex conjugates of each other. But here I'm going to work everything out just to make that point, and then I'll have an s plus 10 here. So I have 3 roots, 2 of which are complex valued, and they're complex conjugates of each other. Okay, so the way to think about this s squared plus 4 is to think about it as being written out in terms of its factors. And I'm going to look at this when thinking about using the Heaviside cover-up method. So the Heaviside method will tell me that to find a, I will need to cover up s minus 2. So I'll have s plus 2j and s plus 10 in the denominator. In the numerator, I have s squared plus 12. And now I need to evaluate it at the root, which is 2j. And I do like to set these up so the first root in one of these complex conjugate pairs is the positive root. It makes it easier to think about later when you start turning things back into cosines. Your mileage may vary. And now to find b, I'll have s squared plus 12 in the numerator again. And now the Heaviside cover-up method will tell me to cover up the s plus 2. So I have s minus 2j times the s plus 10 factor. And then I'm going to evaluate this at s equals minus 2j, which is the root of this denominator. So plugging in 2j here, I'll have minus 4 plus 12 all over 4j times 2j plus 10. And then down here for b, the j's will multiply each other and give me a minus again. And then when I take the minus sign and square that, just gives me a plus. So I get the same thing on top here. I'll still have a minus 4 plus 12. And now down here I'll have a minus 4j times minus 2j plus 10. So let me divide the numerator and the denominator here by 4. So the 4 here is going to cancel, and so I'll be left with a minus 1 plus 3 once I do that cancellation. So I'm left with a 2 in the numerator of each of these cases. And then in the denominator, if I multiply the j through, I'll have a minus 2 plus 10j. And then for b, I'll have minus 2. The j's combine and give me a minus, and when I multiply the minus signs, those cancel. And then I have minus 10j.
All right, so this is 1 over minus 1 plus 5j, and this is 1 over minus 1 minus 5j. I would like to write these in rectangular form, so what I'm going to do is I'm going to multiply each of them by the complex conjugate of the denominator over the complex conjugate of the denominator. So really this is an overly complicated way of writing the number 1, and of course multiplying something by 1 doesn't change it. But now I'm in a situation where I have this nice, happy, complex number in rectangular form sitting here on top. And then in the denominator, the cross terms are going to cancel. Multiplying the minus 1's together is going to give me a 1. And then the j's, when I multiply those together, gives me a minus that cancels that minus. So 5 times 5 is going to give me 25. So I can write this as minus 1 over 26 minus 5 over 26j. And down here, I'll get the same sort of thing. I'll have minus 1 plus 5j, and the same kind of computation is going to give me a divide by 26. So you could write the 26 just once, or you could put it in the real and imaginary parts. It doesn't matter. Either way, notice that these are in rectangular form, and notice, very importantly, as we're expecting, these are complex conjugates of each other. And that's what you get for the partial fraction expansion coefficients when the roots are themselves complex conjugate pairs. So I really could have just done one of these and I would have instantly had the other. But if you have the time, it's good to work them both out explicitly just as a double check on things. Okay, finally, let's do C. So for C, it's easier to use this form of the expression. There's no reason to use the version where we split s squared plus 4 into the individual factors here. So using the cover-up method, we're going to cover up s plus 10, leaving me with s squared plus 12 over s squared plus 4 in the denominator. Now I evaluate this at the root, which is s equal to minus 10. So I'll wind up with 100 plus 12 in the numerator over 100 plus 4 in the denominator. It's 112 over 104. And I figured out off screen that this reduces to 14 over 13, which is approximately 1.077, again, shoved into a calculator off screen. Okay, so if you pull out your calculator and convert these into polar form, you'll see that A is approximately 0.1961 times e to the j minus 1.768. So, of course, B is going to be the complex conjugate of A, and C, we've already figured out, is 1.077, and I'm just copying it up here to make space. All right, so now I can actually invert this Laplace transform. I'll have 0.1961 e to the minus j 1.768 times e to the plus 2jt. You don't have to put the plus there. I'm just doing it anyway. ut plus 0.1961 e to the plus j 1.768. Again, you don't have to put the plus there, but sometimes it helps keep track of things. And then here we'll have e to the minus 2jt ut. Oh, you know, we usually write this as j2. I don't know why I wrote it the other direction here. Same thing. All right, and then we have plus 1.077 e to the minus 10t ut. So unsurprisingly, these first two terms can combine and give me a cosine. So if I take 2, I multiply it by 0.1961, I get 0.3922. Then I'll have a cosine 2t. And remember, to extract the phase, I need to get it from the angle of the complex number sitting in front of the time-varying complex exponential with the positive constant. So I'll have 2t minus 1.768 ut. And then I'll also have plus 1.077 e to the minus 10t ut. You could factor out the ut if you want. Adding my ever-present caveat that this is only for t bigger than or equal to 0. And this is a perfectly fine answer. If you want, you could take this 1.768 and divide it by pi and rewrite it as 0.5627 pi. So often phases are easier to interpret if they're presented as multiples of pi. But you don't have to do that here. It's a perfectly fine answer with the 1.768. Let's double check to make sure if I plug in 0, I get something appropriate. So here I'm actually going to bring over Octave to double check this. So 0.3922 times cosine, plugging in t equals 0, I'll take the cosine of 1.768. So let's say I rounded a bit and made that minus 0.077. If I had the 1.077, I would get, if I plugged 0 in for t and e to the minus 10t, okay, I get 1 back. So that was by no means immediately obvious, but anyway. So the cool thing here is this does indeed match the pre-initial condition I gave at the start of the lecture. So I have this left side continuity. The other thing to note here, and we'll come back to address these issues in quite a lot of detail on a later occasion, is I have this term here that decays with time. All right, it's a decaying exponential. It will eventually die out. It's a transient term. And after that transient term dies out, I'm left with a steady state term. I'm left with this cosine that goes on for all time. And although I won't dig into the details here, in a later lecture we'll see this cosine is the same cosine you would get out of this system if you had put a cosine into it that had lasted for all time. From time equals negative infinity up to infinity, you would get this. You would just get it without this ut. You would have it for all time and not just for t bigger than 0. So your steady state answer here matches with what that original cosine in, cosine out frequency response concept we looked at earlier. And again, we'll come back to this issue in a future lecture.